Okay, so this chapter is very short, only 3 lessons. So that means on Wednesday, next week, you'll have a quiz on chapter 7. And after that is chapter 8 on logarithmic functions. And then after that will be your next unit exam, your third of 4. I sent out the review for trig today, so you'll get that next week. And then you guys will have a chance to do the rewrite the week after Easter, if you want to rewrite the trig exam. Okay, so you'll get that next week. So we're going to look at what the graph of an exponential function does, what its characteristics are, and then we'll also look at some problems that involve exponential growth or decay. The graph of an exponential function, such as y equals c to the x, is an increasing function when c, the base, is greater than 1. It's a decreasing function when c, the base, is between 0 and 1. But it is neither increasing nor decreasing when the base is 1. So from the graph, you can determine characteristics such as domain, range, any intercepts, and any asymptotes. So you'll see that these exponential function graphs will have asymptotes. On the right, it says an exponential function is a function of the form y equals c to the x, where c is a constant, and c will always be greater than 0 for our work in this chapter. X is the variable. Okay, so again, there's graphs there that show the increasing function when c is greater than 1, a decreasing function when c is between 0 and 1. So we're going to see that we're going to be looking at the base graphs, and we're also going to be doing transformations of these graphs. Okay, Cedric? Okay, we're going to be doing transformations of these graphs. So we're going to follow the same principles that we did, where we're going to stretch these graphs vertically, horizontally. We're going to shift them up and down, and we're also going to reflect them about both the x and the y axes. Okay, Logan, are you with us? Okay. All right, so this asks us to graph each exponential function and identify those characteristics, the first one being y equals 4 to the x. So because the base 4 is greater than 1, that means this is going to be an increasing function. And we can see what this graph looks like by setting up a table of values. We can use values of x between -2 and +2. So when x is -2, y will be 4 to the -2, which is 1 over 4 squared, or 1 over 16. When x is -1, y will be 4 to the -1, or 1 over 4 to the +1. Remember, you can't evaluate a negative exponent. You have to make it positive by changing its position. If it's from the top, you go to the bottom, and that changes the exponent sign to positive, which is what we did. 4 to the 0, well, anything to the power 0 is 1. 4 to the 1 is 4. 4 squared is 16. So this gives us some points we can put on our graph. When x is -2, y is 1 over 16. So it's very, very small, but it's positive. When x is -1, y is 1/4. When x is 0, y is 1. We've got the point 1, 4 and 2, 16. So this is the graph of that function. So what happens here is that the x-axis is a horizontal asymptote. The smaller that y gets, it is true that x will get smaller and smaller, but it's always positive, right? When x was -2, y was positive 1/16. When x is -3, y will be positive 1 over 64. And when x is negative 4, y will be positive 1 over 256. So it keeps getting smaller and smaller, but it's always positive. It's always greater than 0. And so the line y equals 0, which is the x-axis, is a horizontal asymptote. The other characteristics that we'll talk about are the domain. The domain of this would be from negative infinity to positive infinity. Because the graph goes left and right forever, there are no restrictions on x. The range is that y is greater than 0, from 0 to positive infinity. And remember that the rounded brackets means that the n values are not included. If they are, we use square brackets, but in this case, they're not. So the domain of these is never going to change. It's always going to be all real numbers. Every value from negative infinity to positive infinity. But the range will change. If the graph is moved up and down, that will change the range. So if we have a d value on the end, the range will change. Okay, so we've stated the domain and the range. It asks us to state the intercepts if they exist. Well, there is no x-intercept because the x-axis is an asymptote. If the graph shifts down, though, you'll get an x-intercept. So we'll see examples of that. There is a y-intercept, and that is the point 0, 1. Remember, the y-intercept is always where x equals 0. And again, that can change. If the graph is vertically stretched, that'll change the y-intercept. If it's reflected over the x-axis, that'll change the y-intercept. If it's shifted up or down, that'll change the y-intercept. So the y-intercept can change.
Sorry for the interruption. Could we have all first responders go to room 1045? Once again, all first responders, please go to room 1045.
Sounds like a code blue. I'm sure that's bad. All right, and this is an increasing function because the value of c is above 1. As you go left to right, the graph is increasing. And we do have an asymptote. We have a horizontal asymptote. And it is a line, so you have to have an equation. An equation has an equal sign and it has a variable. The equation of the horizontal asymptote is the line y equals 0. Every point on that line has a y value of 0. The x values will change, but the y values are always a constant. Right, so there is that graph and the characteristics. On the next page, we're going to graph f at x equals 1/2 to the x. This is a decreasing function because the base c is between 0 and 1. So again, we'll do this by setting up a table of values. We'll choose different values for x, like -2, -1, 0, +1, and +2. When x is -2, 1/2 to the -2, well, again, you got a negative exponent. We need to make it positive, and if we take the reciprocal of the base, the reciprocal of 1/2, which is 2 over 1, that changes the exponent sign to positive. So 2 squared, 2 over 1 squared is 4. When x is -1, it'll be 1/2 to the -1, which is 2 over 1 to the +1, that's 2. Anything to the power 0 is still 1. 1/2 to the 1 is 1/2. 1/2 all squared is 1/4. So we've got the point -2, comma, +4. -1, comma, +2. 0, comma, 1. 1, comma, 1/2, and 2, comma, 1/4. Once again, the x-axis is an asymptote. No matter how big x gets, y will continue to get smaller and smaller, but it'll always be positive. When x is 3, y will be 1/8. When x is 4, y will be 1/16. When x is 5, y will be 1/32. So they're getting smaller and smaller. They're approaching a value of 0, but they'll never get there. They'll always remain positive, which is why the x-axis is an asymptote. Right, so this graph will go through those points and head upwards. We'll go through the point -3, 8 and -4, 16, so it'll look something like that. And obviously it's a smooth curve. So the characteristics, the domain hasn't changed. It's all real numbers. It goes from negative infinity to positive infinity. The range also hasn't changed. It still goes from 0, which is not included, up to positive infinity. Again, there is no x-intercept because the x-axis is an asymptote. But the y-intercept hasn't changed from the last one. It's still 0, 1. This is a decreasing function because as you go left to right, the graph is falling. And again, we have a horizontal asymptote defined by the x-axis or the line y equals 0. So most of our graphs are going to be variations of this. Okay? Now, if you're given the graph, you can write the function. You can write out what the equation is. We know that it's going to be in the form y equals c to the x. So some of these you can do maybe by guess and check, but you can also do it algebraically. Okay? If these points that are given, -2, 16, -1, 4, 0, 1, if they are on the graph, that means they must satisfy the equation. So we can determine what c is by subbing one of those points in. The only point we can't use is the point 0, 1, and I'll show you why in a second. But let's use one of the other points. For example, we can use the point -2, 16, which means y is 16 when x is -2. So sub those two numbers into the equation. Now, you want to know what c is, so we need to get the exponent on c to be +1. And you can get that if you raise that right side to the power. That's the reciprocal of the power on c originally. The power on c originally was -2. The reciprocal of that would be -1/2. Now, whatever you do to one side, you have to do the same thing to the other, so we also raise that to the -1/2. And the reason this works is because on the right side, -2 times -1/2 is +1. That's why we use the reciprocal. And when you have one exponent raised to another, you multiply the exponents, right? So that's why we raise to the -1/2, the reciprocal of -2, because when we multiply them out, we get +1. And on the right side, this will be 1/16 to the +1/2. +1/2 means square root. So it's 1 over the root of 16, or 1/4. So we're saying that that equation is y equals 1/4 to the power x. So I did that using the point -2, 16. Or I could also use the point -1, 4. In fact, that one's going to be a little bit easier. If I use the point -1, 4, I'll get 4 equals c to the -1. I will raise both sides to the power -1. So then I get c to the +1 on the right, equaling 4 to the -1, which is 1/4. Same value. Remember we said you can't use the point 0, 1, and we'll show you why that doesn't work. we start with y equals c to the x and we use the point 0, 1, let x equal 0 and y equal 1, well, on the right side, you get c to the 0, which is 1. And so it gives us a true statement, but we no longer have a c. Remember, we're trying to figure out what is c. Well, if you use the point 0, 1 in the equation, c's gone. So you get a statement that's true. Sure, 1 does equal 1. Remember, we're trying to find the value of c. So this is the reason why you cannot use the x-intercept, where y is 0. This graph was a decreasing function, so that told us that our value of c had to be between 0 and 1, which we did get. This next one is an increasing function, so the value of c has to be greater than 1. And we can find it, and the easiest way to do it would be use the point 1, 5. When x is 1, y is 5, so you get c to the 1 equals 5, or simply c equals 5. And the equation would be y equals 5 to the x. Again, this is an increasing function, so c had to be greater than 1, and it is. You could have got the same thing using the point 2, 25, but the point 0, 1 wouldn't work for us. We'd get at the end 1 equals 1, which is true, but it doesn't tell us what c is. So one of the applications of exponential functions is something called exponential growth and decay. So these exponential functions can be used to model exponential growth when c is greater than 1, and when c is between 0 and 1, exponential decay. So exponential growth occurs when you have an increasing pattern of values that can be modeled by a function of the form y equals c to the x, where c is greater than 1. Exponential decay is where you have a decreasing pattern of values. They can be modeled by y equals c to the x, where c is between 0 and 1. One of the terms we're going to see when we're talking about exponential decay is the half-life. It's a length of time for an unstable element to spontaneously decay to 1/2 of its original value. So an example of exponential decay is where you have a radioactive sample that decays. So in this case, the radioactive sample of radium Ra-225 has a half-life of 15 days. The mass m in grams of this radioactive sample remaining over time, t, in 15-day intervals can be modeled using that exponential graph shown. Question A says, what is the initial mass of the sample at the beginning? And so that's at time 0, and according to the graph, that is 1 gram. At time 0, the graph starts at the point 0, 1. What value does it approach as time passes? Well, it approaches a value of 0 grams. But what you have to realize here in this case, it'll never get to 0. The amount remaining after each 15-day interval is half of what you had before. So after one 15-day interval, you had half a gram. After two 15-day intervals, you had a quarter of a gram, and then an eighth, and then it'll be a 16th, and then a 1/32nd, and then a 1/64th. So those values are always going to get smaller and smaller, but they'll never be 0. If you take half of something, you're always going to have something. Now, it is true that eventually the amount remaining will be so small that it probably won't be detectable anymore, but it's still there because you're always going to have half of what you had before. What is a domain and range? Now, in this case, we're talking about an actual scenario, a real-life application. So our domain and range is going to change, especially our domain, because it's going to start from 0 and go up to infinity. Our range will be between 0 and 1. The 1 is included, but the 0 isn't. Because again, it'll never get to a mass of 0 grams. It'll get infinitely close to it, but never get there. So there's our domain and range. Part C asks us to write the exponential function. So again, it'll be y equals c to the x. And we can find out what c is by plugging in one of the points. Let's use the point 1, 0.5. So x equals 1 when y is 0.5. And so c equals 0.5. And the equation will be y equals 0.5 or 1/2 to the power x. And we're going to see as we go through this chapter as well as in chapter 8, whenever you have a half-life, whenever the amount is being cut in half every so many days or so many hours or so many minutes, whenever that happens, the base is always going to be a half. Okay, so there's part C. Now part D says estimate how many days it would take for the radium to decay to 1/30th of its original mass. So if we use the exponential function y equals 1/2 to the power x, y is the amount at the end, and it'll be 1/30th of what we started with. Now, technically, we started with 1 gram, so it's going to be 1/30th of 1, because that is what we started with. And 1/30th of 1 is 1/30. Now on Tuesday, we're going to learn how to solve exponential equations. We're going to be able to do some of them algebraically by making the bases the same, and we're also going to look at some where you have to solve them graphically on your graphing calculator. This one cannot be done algebraically. We're going to get to that, but again, it involves making the bases the same. You cannot express 1/30th with a base of 1/2. Can't. Okay, so we use our graphing calculator to do that. In equation 1, we'll put y equals 1/30. That's the left side of the equation we're trying to solve. In equation 2, we'll put the right side in brackets 1/2 to the power x. Okay, our domain kind of told us what our x min and max should be. Okay, so if we look at our windows, our domain goes from 0 up to positive infinity. Maybe I'll go from -1, and I don't know what my max should be. Let's put it at positive 10 for now, and I'll set my x scale at 2. My range is only between 0 and 1, so maybe I'll go from -1 up to positive 2 on the y-axis and keep my scale at 1. And the reason I started at -1 is so that I can clearly see where the x-axis is. It's the same reason why I started at -1 for my x minimum. So I'll be able to clearly see where the y-axis is. So when I graph these, it graphs the line y equals 1/30 in blue, and because it's so small close to the y-axis, it looks like it is the y-axis, but it's not. It's above it, because 1/30 is greater than 0. And we want to find the point of intersection. Second function trace, number 5 for intersect, enter, enter, enter. So it looks like 4.906 is what our answer is, 4.906. So x is approximately, and we can make sure by quitting the graph and go x, enter. That'll take my last value of x from my graph. Yep, 4.90, it's actually 907 if we round to 3 decimal places. But this represents how many 15-day intervals. So if we take that decimal, which is in our calculator, and multiply by 15, it'll be the actual number of days. Approximately 73.6 days. That's how long it'll take for the mass of that radium to be 1/30th of what we started with. Okay? This next example, under ideal circumstances, a certain bacteria population triples every week. This is modeled by the following exponential graph. Again, we want to state the domain and the range of this graph. Our domain will be from 0 to positive infinity. Unless the conditions change, this bacteria will just continue to grow. So some things that could maybe stop it from growing: if they run out of a food source, they won't be able to grow. They won't be able to multiply. Or maybe a temperature change kills them off, or something else, some other condition that kills them off. But otherwise, they would continue to grow forever. The range starts with one bacteria, and again, technically that would always continue to grow. The domain is actually the time in weeks, or the range is the number of bacteria. So the conditions changing would change the range, not the domain. But if they all die, then the domain would stop as well, because they can't grow anymore. Part B, write the equation. So again, this is a growth function, so we know that C will be greater than 1. And we can find out what it is by using the point 1, 3, or we could also use 2, 9 if we wanted, but we've seen that it's much easier if you use the value when x is 1, because c to the 1 is c, and c equals 3. So our equation will be y equals 3 to the x. And it's not a coincidence that the base is 3 because it's tripling. That always happens. If the number of bacteria is doubling, then the base would work out to be 2. Okay, it's not a coincidence. It always works that way. So there's our equation. Determine approximately how many days it would take for the number of bacteria to increase to 8 times the quantity on day 1. So on day 1, there are 3 bacteria. So on day 1, there are 3 bacteria. So we want to know what day there are 8 times what we have on day 1. So 8 times 3 would be 24 bacteria. So that means that we're going to have our exponential function is y equals 3 to the x. Y represents the number of bacteria after x days. So in this case here, y would be 24. And we solve this once again graphically. So we're going to have to change our windows for sure here, as well as our equations. The left side of the equation that we're solving is 24, so that goes into y1. Our equation is 3 to the power x, that goes into y2. I'll keep my x windows the same, but my y maximum has to be at least 24 because that is our first equation. Let's change it to 25 and put a scale of 5 on the y-axis. So when we hit graph, hopefully we see the point of intersection, and we do. So we can find out what it is by going second function trace, number 5 for intersect, enter, enter, enter. So it looks like 2.89, but to make sure, if we quit out of there and go X enter, yeah, 2.893. And this is how many weeks. The question wants to know how many days. So if we take that number and multiply by 7, approximately 20.25 days. That's how long it'll take for there to be 24 bacteria, which is 8 times the amount on day 3. Okay? So the questions are not in this booklet, so you will have to bring your textbook for this chapter. And you can work on those questions, so you're free to go to your locker if you need to go get your textbook. So again, we'll be done this on Tuesday, which means Wednesday will be a Chapter 7 quiz. And then next week, again, you will get the review assignment for the trig retest if you want to do that, which will again take place after Easter as well. Okay?